This is Module 12, Lesson 2. This is going to be a very short lesson about light. So I'm starting with this, but I do have some information on the next slide that will help you fill in your boxes. Electromagnetic spectrum is made up of electromagnetic waves. This is on your reference table. Obviously, it's on page 4, as you can see. It doesn't tell you what electromagnetic waves are. If you think about the word, it's waves that have both electric and magnetic properties. So they are composed of both of those characteristics. They travel through space. They can travel through, some of these things travel through things like X-rays. What we're going to start out by doing is just kind of looking at the different types of electromagnetic radiation and make sure that you understand what they all are. Clearly you can see them labeled for you here. You have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Just to point out some places that you see some of these things, you know, radio waves are all around you. Almost everywhere you go, you are surrounded by radio waves. It's obviously what makes a radio work. Other things also work off of that, like your some cell phones work off of radio waves. Your cordless phones in your house may well work off of these. Then you have microwaves, and there's some overlap here for some of these. A microwave obviously works off of microwaves, but other devices too can work off of them, for example, like a cell phone or a cordless phone perhaps. Then you have infrared. Infrared is commonly referred to as IR. Infrared is a heat wave. Things that have thermographic images with them. I don't know if you've ever seen them on like the weather, like a weather forecast. They show you pictures of the clouds, and they use the colors like red, orange, and yellows represent warmer things, and then greens, blues, and purples represent the cooler colors. They can use infrared in order to take those pictures. Next, you have visible light, and as you can see, it fits into this little space right here, and then it's expanded down here at the bottom for us to be able to see it better. Visible light is the only part of the electromagnetic spectrum that you can see with your eyeball. Most people learned it this way. Roy G. Biv, it's the colors of the rainbow. I have that somewhere too for you to write down in just a little bit. So I'll go back over that again. But it is the only portion of this, again, that you can see with your eyeballs. Then you have ultraviolet, most commonly referred to as UV. You know that comes from the sun. It's what causes skin damage. Then you have X-rays, and there's a lot of overlap between these two things. X-rays, of course, are given off by X-rays, like when you go to the dentist and your teeth X-rayed or a broken bone. And then you have gamma rays. Hopefully you're not exposed to many of these. It's what would be used in certain things like cancer radiation treatment. You would find it at like nuclear power plants. As you work your way from radio waves all the way to gamma rays, the energy increases and the waves get more and more dangerous. So energy goes up from radio to gamma, and their deadliness increases basically. You can clearly see that it's labeled here that these have longer wavelengths and these are shorter wavelengths. So you should be able to use this picture to answer questions about, you know, like which type of wave has the longest wavelength? Well, that would be radio. Or if you had to put them in order of longest to shortest or shortest to longest, then you simply just use this picture to answer those types of questions. So here's some details about these waves that should help you fill in some of the boxes on your paper. Electromagnetic waves are waves of energy. You know, they travel at the speed of light. So all of the waves that were on this image right here, they all travel at the exact same speed. The speed of light is listed for you on your reference table. It's on page 1. You have a little table at the beginning of physical constants and symbols and values, and the speed of light is down almost at the very bottom. It says the speed of light in a vacuum, and then it gives you this number. It is 3.00 times 10 to the 8th meters per second. That is really, 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 really fast. That is 300 million meters in 1 second. All of those waves are traveling at the same speed. Now that's in a vacuum. That's why it says up here, the speed of light depends on the medium. And there should be another parentheses there. The more dense the medium is, then the slower those waves are going to travel. Okay. Electromagnetic radiation is emitted from energized matter. It's kind of neat that if you energize like the elements, you will actually see them give off electromagnetic radiation. And what that's referred to is an atomic emission spectrum. I didn't mean to draw on that. There are some pictures, you can Google these all over the place, and you can find the spectra that is given off by every single element. It's kind of like a fingerprint of the elements. They are very, very specific. It's really neat what they give off. To energize them, what they'll do is like run electricity through a tube of like hydrogen gas or helium gas, neon, whatever. They'll commonly do stuff like that. And then you can see that they give off these different band patterns. It's really, really neat how they do it. Okay. All right. A little lesson here on how we see. Just kind of throwing this in here. What you see, there are actually 3 different primary colors of light. What you see is basically what is reflected. You know, if you're in art class, you've been taught that you have 3 primary colors, that you have red, yellow, and blue, or you were taught the Ives color wheel that has cyan, magenta, and yellow. You make everything out of either red, yellow, blue, or cyan, magenta, and yellow. But with light, there's 3 primary colors, that they are red, blue, and green. When you have black, you have the absence of all light, or the absence of all things being reflected. You see nothing. White light is actually when you see them all together. And remember that when you see them all together, you have Roy G. Biv. That's red, orange, yellow, green, blue, indigo, and violet. That's, you know, that's the mixture of all of the colors. When you see them all spread out like a rainbow, you are seeing Roy G. Biv. Those are the colors of the rainbow. Because when you see a rainbow, you see white light that's spread into all of the colors that are going together to make it. What you see is the reflected color. And so I gave you some examples. Like if a leaf looks green, then it's because you are seeing the red and the blue are being absorbed, and the green is what's coming back at your eyeball. If pavement looks black, then, you know, think about black as the absence of all light, then nothing is being reflected from it. It's all being absorbed, so you end up seeing black. If you see white, that means everything is being reflected back at you. And I'm looking at the blanks that are on your paper too, going back to some of the different colors here. I think the thing that I don't see answered for you is about the different colors of light. I'm looking to see if I have anything here. Nope, that's the end of the lesson. So let's see if I can fill those in for you. Go back to this. So I'm down towards the bottom of your page where it says different colors of light have different blank and blank. So basically, different colors of light have different wavelengths and frequencies. That's what should go into the blanks. And you can see right here that you have red, orange, yellow, green, blue, and violet. They don't put indigo as a part of this, but they have a different wavelength. So you can see right here, red has the longest wavelength and violet has the shortest wavelength. Sorry, my dogs are going crazy this morning. Why do they have these different wavelengths? Because they do. They travel at different wavelengths, and if they have a different wavelength, but they all travel at the same speed, they're all going 3 times 10 to the 8th meters per second. If they all have a different wavelength, that means that frequency also has to be different. As the wavelength goes up, frequency has to come down in order for V to stay the same. So red will have the, if it's got the longest wavelength, it's going to have the smallest frequency. And if violet has the highest wavelength, then it's going to have the lowest frequency out of the colors, okay? So we can use this in some of our later lessons to see some different things, okay? So now we are truly at the end of the lesson. Now what, you know, no practice sheet. Make sure that you have the stuff in your brain, that you understand it. You're going to be quizzed on it. So just be prepared because you need to. Let me know if you have questions.